Welcome to the module Creating Flexible Joints. In this module, you will learn about flexible joints. Flexible joints allow mates to behave more realistically than conventional mates because they account for backlash or play, which is unintended motion caused by gaps between parts. To better understand flexible joints and why they are used, you will create a set of flexible joints. You will also plot a parameter called yaw to analyze how flexible joints affect motion. In this module, you will learn how to define flexible connectors, bushings, in SolidWorks Motion. You will also learn how to create a rack and pinion mate and a lock mate. Along with that, you will learn how to create advance plots. This module is divided into several topics. Click the topic titles in the list for a brief overview of each topic. The model that we will examine is a geometric representation of a short long arm SLA suspension subsystem attached to a steering mechanism. An assembly like this would be seen in an automobile. We will simulate this assembly being driven on a test track, which has rumble strips that are 50 millimeters in height and spaced 2,100 millimeters apart. The vehicle is moving at a speed of 60 kilometers per hour. The goal of this module is to inspect the toe angle that the wheel exhibits throughout its vertical travel of 50 millimeters in jounce and rebound for both rigid and flexible joints. The solution to the defined problem is divided into the following steps. 1. Create mates. 2. Define the motion. 3. Plot the results. 4. Modify the joints so that they are flexible. 5. Rerun the study. Let us see how to apply a rack and pinion mate and a lock mate to the assembly. Click Show Me to launch a demonstration video. We have opened the file titled Steering Suspension System.sldasm for you. Before we create a motion study, we need to examine the assembly and determine how the linkages are connected. To do so, scroll down and expand the Mates folder. Scroll down and click the Angle 5 mate. This mate controls the angle of the steering wheel and will be one of our study parameters as we can use this mate to turn the steering wheel to specific angles. However, no mates currently exist to connect the wheel with the tires. A rack and pinion mate will be created, allowing the tires to turn once the wheel is rotated. Move the tire vertically and rotate it. Notice that the lower arm is not connected to the lower strut. Also, notice that the tire has turned, even though the steering wheel does not because of the angle mate. Scroll up. The 5 base caps are fixed and cannot move. Fixed parts are preceded by the letter F in the feature tree, while floated parts, which can move, are preceded by a dash. Now we will add 2 mates to the assembly, a rack and pinion mate to connect the steering rack to the steering shaft, and a lock mate to connect the bottom of the strut to the lower arm. This lock mate will bond the strut to the lower arm and represents a rigid connection by components that are not explicitly modeled in this assembly. Before applying these mates, the tire needs to be turned to its original 0 position. To do that, close the assembly without saving, and then reopen it to return to the starting point. Alternatively, use Reload to copy the assembly on the disk back into RAM. We will use the second method to bring back the tire to its original 0 position. Click File, and then click Reload. Click OK, and OK again to reload the assembly with starting point. Let's add a lock mate between the lower arm and base caps 5. Click Mate. Then, click Lock. Now, select the part Lower Arm and Base Caps 5. Again, this lockmate represents a bonded connection between the lower arm and the strut by parts that are not explicitly modeled in this assembly. Click OK. Base Caps 5 was fixed when we opened the assembly. Now that we have created the lockmate to the lower arm, we must remove the fixed mate to allow the suspension to move. Right-click Base Caps 5 and click Float. Now we will add a rack and pinion mate between steering shaft and steering rack, which would be connected through a worm gear. Click Mate. Then click Mechanical Mates. And click Rack Pinion Mate. For rack selection, select the face of the steering rack, and for pinion gear selection, select the face of steering shaft. Click Rack Travel Revolution. When the steering wheel rotates by 7 degrees, the steering rack part should travel by 1.0 millimeters. That means the steering rack should travel by 51.43 millimeters per revolution of the steering wheel. Enter 51.43 millimeters. Click Reverse to make the direction correct, and click OK. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about applying mates. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. A simple harmonic motion will be imposed on the tire to simulate rumble strips. Frequency can be calculated using the spacing of the rumble strips and the velocity of the vehicle. Let's consider that the vehicle is traveling at 60 kilometers per hour and the rumble strips are placed 2100 millimeters apart. Using these values, frequency of the simple harmonic function is 7.94 Hz. We can also assume that the height of the strip is the amplitude of the simple harmonic motion and its value is 50 millimeters. Let's see how to create a motion study and set oscillating motion to a motor. Click Show Me to launch a demonstration video. Right-click the Motion Study 1 tab and click Rename. rename the motion study to tire. Ensure that motion analysis is selected as the type of study. We will add a motor to drive the vertical motion of the wheel based on the frequency of the vehicle moving over the rumble strip at the desired speed. Click Motor. Specify linear motor under Motor Type. Select the vertex in the center of the wheel hub for the position of the motor. For direction, select the top plane in the part Wheel. We must select top plane in the wheel part and not a plane outside of the part. For motion type, click the drop-down and click Oscillating. Enter displacement of 50 millimeters and frequency of 7.94 Hz. Keep 0 degree as the phase shift and click OK. We have turned the assembly. Now we will create a spring with damper between lower and upper strut. Click Spring. For spring endpoints, select the vertex of the sketch rectangle and the edge at the bottom of the strut. Ensure that spring type is set to linear spring. Enter 60.0 newtons per millimeter for the spring constant. And 405 millimeters for the free length. Click Damper to add a damper. Ensure that damper type is set to linear. Scroll down and set damping coefficient to 0.46 newtons per millimeters per second. For display, ensure that the coil diameter is entered at 60 millimeters. Number of coils is 10 and wire diameter is 10 millimeters. Remember, values entered in the display section are used as graphic parameters only. Click OK. Now, we will modify the motion study properties to record 500 frames per second. Click Motion Study Properties. Enter 500 frames per second. Click OK. We will now set assembly key to 0.12 seconds. This will allow the tire to move up and down once. Right-click Key Properties. Click Edit Key Point Time and enter 0.12 seconds, which is one cycle at the input frequency of 7.94 Hz. Click OK. Calculate the study. This dialog window suggests that the study might be too short. However, because of the number of frames we will be calculating, the study time is adequate. Click Yes. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about creating a motion study and setting oscillating motion to a motor. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. In the automotive sector, toe angle can be defined as the symmetric angle that each wheel makes with the longitudinal axis of the vehicle. The toe angle is expressed in degrees. Toe angle is of two types, toe in and toe out. If you look at the vehicle from the top and the leading edges of the front pair of wheels are pointed towards each other, then the wheels are toe in. If the leading edges point away from each other, then the wheels are toe out. Please note that in the images, the pink arrow denotes the direction of travel of the car. Toe settings affect three major areas of performance: tire wear, straight line stability, and corner entry handling characteristics. Let's see how to create plots and examine the results. Click Show Me to launch a demonstration video. Let's play back the study at slow speed to observe the motion. Click Play. Now, we will create the yaw plot. This will help us better understand the toe angle. Click Results and Plots. Specify other quantities, pitch, yaw, roll, and yaw. Select the tire face of the wheel for the part to create Results section. This will plot the yaw at the center of mass for the wheel. Click OK. The toe angle can easily be determined from the plot. We are interested in creating a plot of toe angle as a function of the vertical displacement of the spindle. To do that, let's edit the previous plot. Right-click Plot 1 and click Edit Feature. Under Plot Result, select New Result. Select Displacement, Velocity, Acceleration, Center of Mass Position, and Y component. Select the tire face on the wheel as the part to create the result. Click OK. Let's examine the plot. Because we have rigid joints, we have two lines that fall on top of each other. One line is the wheel moving up, while the other is the wheel moving down. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about plotting and examining the results. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed this simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. In the physical world, nothing is absolutely rigid as materials have the ability to deform elastically and plastically. Up till now, the case study of the SLA suspension and steering mechanism was solved with an assumption that the joints used in this study were all rigid. To simulate the actual behavior of the model, you need to apply the flexible joints. In SolidWorks Motion, bushings are the flexible mates. Bushings are added to model flexible mates used on physical suspensions. Bushing elements allow deformation by some amount. Typical bushings used in automotive vehicle design consist of steel-on-steel, urethane, or nylon. The stiffness and damping characteristics of these bushings are measured by SAE testing methods. You can apply isotropic and orthotropic bushings. Isotropic bushings apply uniform bushing properties in all direction. In case of orthotropic bushing, you can specify different properties in each direction. Orthotropic bushings can greatly affect the kinematics, such as camber and toe angles, and dynamics, such as joint and shock forces, results of your model when compared to a rigid connection. In our simulation, we will use isotropic bushings. Let's see how to solve the motion study with flexible joints. Click Show Me to launch a demonstration video. Let's review the mates associated with lower arm and upper arm. Click Play. Notice how they are connected to the base caps. The base caps are connected to the automobile frame. There is no slack in the mates. However, in real life, there is some slack or play between the arms and base caps. To incorporate this slack, a flexible connector, or, in other words, a bushing, will be used. We want to edit the global mates locally, so we must edit the mates in the SolidWorks Feature Manager design tree while staying in the Motion Study tab. Scroll down and locate Concentric 2 mate in the Mates folder. To edit it, right-click Concentric 2 and click Edit Feature. Click Analysis and click Bushing. Ensure that isotropic is selected for translational. For translational, change the stiffness to 3,500 newtons per millimeter. Damping to 2.63 newtons seconds per millimeters, and keep the force value to 0 newton. Ensure that isotropic is selected for torsional. Leave the values at their default settings and then click OK. You can see that Concentric 2 has a bushing symbol next to it. We will repeat the same process and add the bushings to the other mates Concentric 4, 13, and 14. Now that the bushings are added between base caps and arms, we will run the study. Click Calculate. On examining the plot, we can confirm that the toe angle is affected by the bushings. Let us review the simulation. Zoom in to the location of the lower arms where it connects to the base caps. Now we will play the study at slow speed. Click Play. Notice how lower arm interacts with the base caps. There will also be some slack between the moving parts and base caps. Click Save and click Close. That brings us to the end of this demonstration. Click Next to continue. Now you take the controls and find out how much you have learned about solving the motion study with flexible joints. Click Try It to launch the simulation and go through the steps on your own. Congratulations, you have successfully completed the simulation. Click Next to continue. Here's a question to check your understanding of what has been covered so far. You've reached the end of the module, Creating Flexible Joints. Here are the key takeaways from the module. Click each tab to learn more.